Hi, welcome back. Today we have a question which is the pressure rise from the free stream to the nose of a fuselage section of an aircraft is measured in a wind tunnel of 20 degrees Celsius to be 34 kilopascal with the wind tunnel airspeed of 900 kilometer per hour. If the test is to simulate flight at the elevations of 12 km, what is the prototype velocity and the expected nose pressure rise? So the question asks is what's the prototype velocity and the expected pressure rise? Okay, so the first step, we need to list out what the given for the model and the prototype. So step number one, what's the given for the model as well as for the prototype? What's the parameter given here? The given here, the aircraft is measured in a wind tunnel. Remember, wind tunnel focus on the model. So temperature of the model to be 20 degrees Celsius. And then the pressure of the model to be 34 kilopascal. So it's the same here. TP and the PP. Temperature of the prototype not given. And then the pressure of the prototype not given as well. And second step is for similarity to exist, we need to look at the dominant effect. You can see here, the wind tunnel speed is 900 km per hour. This is definitely more than 0.3 Mach number. So this is under compressible flow. When it is under compressible flow, we're going to use the common dimensional analysis of Mach number. So we need to equate the Mach number. Alright, so Mach number of the model equal to Mach number of the prototype. So the formula of Mach number is velocity of the model over the speed of sound, the local speed of sounds at that location. So over C. So here C, we expand further, become C equal to KRT of the model equal to velocity of the prototype over the speed of sound of the prototype, KRT of the prototype. Remember that the gas constant conducted at air, in the air, KR of the model, the same what with the KR of the prototype. So cancel out this one, cancel out this one. We arrange, alright? We arrange here, what's the prototype speed? The question asks the VP. So we need to get this VP here. So arrange VP to be the subject, VP equal to, alright, the square root of TP over TM multiply with VM. So what's the temperature of the prototype? Alright, the temperature of the prototype, it is given here. The test is to be simulate flight. The test is to simulate flight. This is the real prototype at the elevations of 12 km. So elevation, this is Z. Alright, this elevation of the prototype to be 12 km. Alright, this is actually the standard gas property. When you look at the table under the fluid mechanic one, the book of Porter, you can look at table 6, table B.3 at the appendix section. Table B.3, you can find the temperature correspond to this elevation to be 216.7 Kelvin. This is basically the temperature correspond to this elevation. You can look at the appendix section under table B.3. Okay, so temperature of the prototype given here 216 Kelvin. This is in the unit of Celsius. Convert to the SI unit, which is Kelvin. You need to plus 273 plus 20, which is 293. Okay, substitute here. Temperature of the prototype, which is from the table 216.7 Kelvin over temperature of the model 293 Kelvin. Multiply with the velocity of the model. Okay, here we look at here. Okay, the velocity given here is 900. This is the speed of the model. So Vm 900 km per hour, convert to SI unit, you will get 250 meter per second, because 900 multiply with 10 the power of 3 over 3600 seconds, you will get this number. So straight away substitute 250 meter per second. Definitely you will get the final answer to be 215 meter per second. Alright, so this is the speed of the prototype. Step number 3. Okay, for similarity to exist, we need to equate the pressure drop using the Euler number. Right? For similarity to exist, we equate pressure drop using Euler number. Alright, so the Euler number is rho v squared. So here we start with the model. Euler number for the model equal to Euler number for the prototype. So the formula of Euler number is delta P, the pressure drop or pressure rise, over with rho v squared. This is for model, this is for model and model as well. So delta P of the prototype over rho of the prototype and velocity of the prototype squared. We know that here, okay, here the density is not the same because having different elevation. Alright, the density of the model and basically the density of the model we consider as a reference elevation is 0 will be different with the density of the elevation 12 km from the ground. So in this case, we need to refer to table B.3 under the appendix section. Okay, under refer appendix section. Appendix section, go to table B.3. You will find out that the density of the prototype at 12 km from the model to be from the ground to be here, 12 km from the ground to be, alright, 0.3119. Okay, the density of the air. This is kilogram per meter cubic. And then the density of the model at 0 kilometer on the ground will refer to 1.225 kilometer per meter cubic. Right, the density of air is not the same, yeah, having the different elevation. So from here, you need to substitute and arrange as well. So equate back the Euler number, which is here. You need to arrange. Alright, you need to arrange this form. You can arrange to be, you can get the delta P of the prototype. Arrange back. This one, you move other side, you will get rho P VP squared over rho M VM squared multiply with rho P of the model. So just substitute this part. Okay. So from here, rho P of the prototype equal to density of the prototype, which is here 0.3119 over width 1.225 multiply with VP, velocity of the prototype, which is 215. Okay, 215 squared, this is squared, over V, velocity of the model, which is 250. 900, remember 900 kilometer. Multiply with delta P. Okay, the pressure drop here. Given the pressure drop, the pressure rise here at to be 35 kilopascal. This is the pressure of the model, 34 kilopascal. Okay, substitute here. 34 kilopascal. So the final answer would be 6.4 kilopascal. Therefore, that is the final answer.